Hey guys, welcome to your first unit in calculus. Look at you, fancy math monster. You're going to pause the video and read up to this part, and then we'll come back together and chit chat. So go ahead and pause the video. See you in a second. Hello, welcome back. So while you were reading, you should have seen something mentioned called average velocity. And you might remember average velocity from physics, right? The only real difference between average velocity and speed is that we can find average velocity with the change in distance over the change in time. And the only difference between speed and velocity is that velocity has direction and it can be negative. So if an object is dropped from an initial height of h sub 0, we can use the position function s of t equals negative 16t squared plus h of 0 to model the height, s, in feet of an object that has fallen for t seconds. So let's go ahead and read this example. I don't know if any of you even remember who Wile E. Coyote is anymore, but he was like a famous character on these like Saturday morning cartoons that were popular, probably when like, I don't know, my older sister was younger and basically this coyote guy is always trying to catch the roadrunner and eat him, but he befalls all these horrible things and he like falls off cliffs and pianos fall on his head and it's a whole big thing. So let's examine the position function in the context of Wile E. Coyote and his poor misfortune. So Wile E. Coyote, once again trying to catch the roadrunner, waits for the nastily speedy bird atop a 900-foot cliff. Go ahead and highlight 900-foot cliff because we gon' use that. With his Acme rocket pack strapped to his back, Wile E. is poised to leap from the cliff, fire up his rocket pack, and finally partake of a juicy roadrunner roast. So we have Wile E. Coyote, and he's standing here, and he's got his little jetpack on. He's ready to go, and he's so excited. This looks like a human being and not a coyote, so let's give him a little bit more of a coyote face. Okay, now he looks like an alien. Whatever. So seconds later, the roadrunner zips by and Wile E. leaps from the cliff. Alas, as always, the rocket malfunctions, oh no, and fails to fire, sending poor Wile E. Coyote plummeting to the road, disappearing in a cloud of dust. So this cliff is 900 feet tall, and poor little Wile E. turns into a cloud of dust at the bottom. So sad. What is the position function for Wile E. Coyote? So let's use the position function given up here. This guy, we're going to use it in the context of the problem. So we've got s of t is equal to negative 16t squared plus the initial height. And remember, they said that it's a 900-foot cliff, so that's going to be our initial height, h of 0. Okay. So if we went ahead and graphed that, we would get something that looks like this, standard parabola. Hey there. Great. So part B says find Wile E's average velocity for the first 3 seconds. So when time starts to about 3 seconds in, so maybe like here or something like that, we want to find the average velocity. So we would be finding basically the slope between 0, s of 0, and 3, s of 3. Okay, so we're finding the average velocity between these 2 points. So we would have, to find average velocity on a graph or between 2 points, you would do s of 3 minus s of 0 all over 3 minus 0. So it's the change in y, or feet in height, or height in feet as a function of time, over the change in x. It's just slope, right? So if you want to go ahead and look at your graph, pull up a table, and find your bottom of the time interval and then the height at that time to your top of your time interval and then the height at that time, you could just substitute those into the formula. So I would get 7, s of 3 was 756 minus s of 0 was 900 over 3 minus 0. I would do the math and get negative 48 feet squared, feet per second, sorry. So you'll notice that since velocity is negative, that's indicating that the poor coyote is falling. And that makes perfect sense in the context of our diagram. Part C, find Wiley's average velocity between time equals 2 seconds and time equals 3 seconds. So now we're changing it. We're finding it from, this is going to be a little closer to the when time is 3 seconds. We're finding 2 comma s of 2. And we're finding the average velocity between those 2 points, okay? So we're going to use the same formula for average velocity, except this time it's going to be s of 2 minus s of 3 is the top interval, and then minus s of 2 over 3 minus 2. So you go ahead and pull up the table and look. So s of 2 is going to be 836. So now we're going to have s of 2 is 836, s of 3 is 756. So we would do 756 minus, what was the second one? 836. All over 3 minus 2 is going to be 1. So I'll go ahead and get negative 80 feet per second. Okay, so that is the average velocity between time is 2 seconds and time is 3 seconds. So if you go ahead and look at your graph, that was our average velocity between 0 and 3. This is our average velocity between 2 and 3. Okay, so notice that the line segment is getting shorter, joining the 2 points because the time interval is shrinking, right? Our distance along the x-axis or the time axis is shrinking. So let's look at D. Find Wiley's velocity at the instant t equals 3 seconds. At the instant t equals 3 seconds. Well, I can go ahead and look at the table, right? And I can look at 3, and it says that the height is 756. But if I'm trying to look at the instant, you'll see that there's like nothing I can compare it to. If I'm trying to do the change in y over the change in x to find the average velocity, there's no second point that I can subtract to find that average velocity. So this is where we come in with limits, okay? The problem with part D is that we're trying to find the instantaneous velocity, and without the concept of a limit, we cannot find the answer to part D. Using a limit to solve this problem involves studying what happens as we get super, super close to 3 seconds, but we aren't just at 3, because then there's no change occurring, okay? So in these ones here, we have example, 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 example. You're finding the average velocity between increasingly small time intervals. 2.5 to 3 seconds, that's only a half a second. 2.9 to 3 seconds, that's only a tenth of a second. And it gets shorter and shorter, the space in between the two times, until that time interval is basically approaching one particular instant. Okay, so what you're going to want to do is set yourself up a little chart. Okay, so you're going to go ahead and find the average velocity here. You're going to find the average velocity here. You're going to find the average velocity for this time interval. And you're going to see what y value the function is trying to approach. Okay, you're going to see what average velocity we are trying to approach at the particular instance when t equals 3. Okay, sorry, talking right at the same time. I was like stopping. Okay, and then for the last one, s of 3 minus s of 2.999 over 3 minus 2.999. Okay, so go ahead and pause the video, find all of those calculations. They could be really laborious if you don't use one special trick. So you're going to want to pull up the graph of the position function, right? And then to find the average rate of change, you're just going to go Control T, and then Control 6 should put the table on the next page. So you do Control 6, and then it should put the table on the next page for you, okay? So you can use these calculations but you're also going to want to do like, you're going to set it to ask. Okay, so you go menu, table, and then you do edit table settings. And then you're going to change this from auto to ask. Go, 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 go. No, 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 no. Stop it. It's like frozen. There we go. Okay, now it's an ask. Got it. Come on, stay. Okay, so now you can type in the things that you're looking for. Okay, so you could do 2.5. We already know what S of 3 is, but what's S of 2.5? Oh, it's 800. Okay, so now I can go ahead and put that in here. You can do 2.9. You can do 2.99, so on and so forth. Okay, this will help you get the inputs for your average velocity much faster than doing it by hand. So pause the video, calculate those, and come up with the average velocity as we approach t equals 3 seconds. Go ahead. Pause the video. And great, you should have gotten negative 88 feet per second for this interval. You should have gotten negative 94.4 feet per second for this interval. You should have gotten negative 95.8 feet per second for this interval. You should have gotten negative 96 feet per second for this interval. So we should see that as t gets closer and closer and closer to 3, we approach an instantaneous velocity of negative 96 feet per second. So even though we can't find the average velocity at exactly t equals 3 seconds, we can discover what Wiley's velocity is approaching at t equals 3 seconds. So what is a limit? The limit of a function is the y value that the function approaches as x gets closer and closer to a specific value. So the way that I always think about it, right, is it's the y value our function wants to reach. And this may not make a whole lot of sense to you at this stage in the game, but let's look at an example and see if that puts it into a little context for you, okay? So here it says, example number 1, sketch the graph of f of x equals 2x minus 3. So we know how to do that. We are going to do a y-intercept of negative 3. Slope of 2. Okay. You could also just graph this and pull up the table, but it's probably faster to just do it in your head. This is our f of x. Hooray. So you're using the graph, and we have choice A. What is f of 2? F of 2 is going to be the function evaluated at 2. So we have 2 times 2 minus 3, and that's going to give me 4 minus 3, which is just 1. So what we're going to do is write the limit as x approaches 2. We say this as the limit as x approaches 2 of f of x, this is f of x, equals 1. The y value that the function wants to approach as we get to 2, so we have 1, 2, is 1. Okay? So part B says, complete the table of values below to determine what happens as x gets close to 2. So now we're thinking in terms of as x approaches 2 from the left, notice how all these values are to the left of 2 on the number line, and they get increasingly closer and closer and closer to 2 as we approach from the left, right? So we start by getting to 1.5, right? And then we get closer and closer and closer and closer and closer and closer and closer until we get right next to 2. 1.99999 is right next to 2. And then on the other side of the table, we're going to examine what happens as x approaches 2 from the right. So as x gets closer and closer and closer and closer and closer and closer and closer to 2. Okay, so I want you to think about limits as having two sides. You know how people always say there's always two sides to every story. There's always two sides to every limit, okay? So remember that. Let's see. You are going to type 2x plus 3 into your calculator, okay? And we're going to do it the same way that we did this one, okay? So we have control add a page. Oh, no, it's not on the screen. There we go. the way that I'm like sharing the video, it won't let me like get to the computer screen. Let's do handheld side screen. All right. You only live once. Do it live. Okay, here we go. So we have 2x minus 3. Go ahead and change that. 2x minus 3. And then we're going to pull up the table, Control T. And then we're going to do the exact same thing that we did before. Okay. So we are going to go to Control T, Control 6, puts it on a new page for me. Go over to the new page. Okay. And then you're going to go to Menu, Table, Edit Table Settings, change this to Ask, hit OK. And then now we can look for all the values that we want on this chart here. So we've got 1.5, 1.75, 1.9, 1.5, 1.75, 1.9, and then I think it just gets increasingly close to 1.99, 1.999. Okay. Okay. So we've got all these great things here, and we can go ahead and put them in our table. So 0, 0.5, 0.8. 0, 0.5, 0.8. 0.98, 0.998. Okay, so what y value is the function trying to get to? What y value is this trying to get to? It's getting so close to what? 1, right? All right, let's go ahead and do the same thing on the other side. So now I have 2.001, 2.01, 2.1, 2.25, and was that it? Oh, 2.5. Okay, so we've got 2, 1.5, 1.2. 2, 1.5, 1.2. 1.02 and 1.002. So what y value is the function trying to get really close to as we approach 2 from the left and the right? The y value that it wants to achieve is 1. Okay, so go ahead and pause the video, complete this next example here on your own, complete the next example here on your own, and then tie it all together by reading the definition of a limit as x approaches a.